Okay, excuse me. So last class, we went over equal payment series, right? I'm just going to do maybe just a brief recap. Try not to go into that much detail. And so if you remember, for equal payment series, we said we have shortcuts. We have nice little formulae that we can use in order to find either P or A or F, depending on the situation, right? And so we had these four cases right here. And oh, actually, let me just do something. No, never mind. I mean, that might change things on your end. Okay, so we said we can find either F, we can find A, or we can find P, depending on what we have and what sort of situation we're working with. Like, what is the context of the problem? Is it a loan? Is it a savings account, an investment, etc.? And then we had this case where we had a special case where n goes to infinity. Okay, and we gave formulae for each of these cases, and we saw that they're kind of related, and you can sometimes derive one from the other one. And so that covers everything that relates to equal payment series. Okay, and we went through all of these in detail. So actually, I think because I'm noticing a lag with my pen, so I need to switch to presenter mode instead of full screen mode. So give me just a second while I do that. So you may, well, actually, I don't know if, oh, okay, yeah. So screen should be gone from your end. Now I do full screen and then switch to presenter view. And now I'll share again. So let's see if this works. I should have done this before. Okay, so hopefully the screen is back now. Okay, and so we went over all of these cases and we said, yes, it is. Okay, great. In this class, we're going to be switching to something different. And also, it's a special case or a pattern, let's say, of cash flows that we can derive nice formulae for. So that makes, again, our lives very easy when dealing with these types of cash flows. So in particular, we're going to be looking at something called a gradient series. Okay? And you may know what the word gradient means, right? Especially like if you use, I don't know. Well, I mean, you could have seen like gradient in math, but you could have also used like gradient colors in, let's say, Word or PowerPoint, where the color changes from left to right, for example. And there's a gradient, meaning like darajat, as you go from left to right, okay? So that's what gradient roughly means. And there are two types of gradient series that we're going to be talking about. And so the first one is called linear gradient series. You may also see this sometimes called arithmetic. At least I think this would be referring to the same type of series. And also sometimes just uniform. No, actually not uniform. No, never mind. That's a different thing, right? So arithmetic and linear gradients, they should be the same thing. And what this means is something that looks like the following. So here we have our cash flow diagram, right? And we start at time 1. Now let's say we have a payment A1. Remember A sub n, right? Where n is the time period. So the A1 means the payment or the income in this case at time 1, okay? And now in a linear gradient series, what's going to happen is that at time 2, your payment or your income, if I say payment and the arrow is pointing up, I mean, you know what I'm saying, right? So don't be a stickler for the actual word income versus payments. Your payment at time 2 is just going to be the payment in time 1 plus some number G, capital G, okay? And at time 3, it's going to be the payment at time 2 plus an additional G. So your payment from time period to time period keeps increasing by this constant amount, capital G. And as you can see, we can write a simple formula, right? So the payment at time n, so if I want to write like A sub n, is just going to be A1 plus n minus 1 times G. That's in general. You see here, for example, A sub n, the payment at time period n is just A1 plus 8 minus 1, n minus 1 times G, right? And so this is kind of what it looks like. And it's called linear because as you see here, the line is sort of, well, the increase takes a linear shape. It just grows by the same constant amount. And you can even like think about it as having a constant slope, which is capital G. right? And so that's why this sort of series is called a linear gradient series, okay? So this is one type of series. The other one is called the geometric gradient, okay? And so geometric, we've seen this word before, right? When we were talking about that series that we were summing in the last class, right? Geometric power series is also correct, as it turns out. And so what a geometric series is that in time period 1, you start with some value, a1. However, the increase is no longer just a constant amount, period over period. It's now a percentage, right? So a sub 2 is a sub 1 times 1 plus little g, where little g is some value, okay? So this is some percentage. The g here is a percentage, so it's like between 0 and 1. It's similar, it's very similar to the interest rate. However, notice that here it's something different than the interest rate. So what we're saying here is that these are the actual payments, but they increase. This is not the value of A1 increasing. That's interest, right? A1, if you want to find out its value at, for example, time period 2, it will be A1, 1 plus I, right? Because you accumulate interest I for one time period. So that's A1's value at time 2. What we're saying here is that this is a completely different payment, right? And so all of these are actual payments. However, these payments have a pattern and they increase sort of geometrically, right? And that's why you see this, meaning as a percentage. So each payment increases over the previous one by this additional percentage of G. In this case, little g. So notice here we use capital G for linear gradient, and we use little g for the geometric gradient. Okay, so hopefully the setup is clear. And you see, of course, that the linear one is just a constant increase over time, whereas with the geometric, it's really exponential because it keeps growing faster and faster, which is very similar to the interest rate. Okay, so these are the two types of series that we're going to be talking about today, and we're going to derive formulae for each of them. Before we do that, so first we're going to talk about the linear gradient. However, they outline a very special case here for linear gradient. So as you see, we have a line, right, linear, and each payment increases before each payment increases, like each subsequent payment is the previous payment plus G, right? So G2, G3, G4, G5, G, etc. But here, notice in this case, this particular payment at time 1, the first payment is 0. Whereas here, if you go back to this example that I gave here at time 1, let me erase the pen. The first payment is A1. It's some value. Also, by the way, all of these payments are going to start from time 1. And so when we compute P, it's going to be at time 0. It's very similar to the interest rate, right? So P is going to be here when you compute it. So P is going to be one time period before the first time period, before the first payment in the series. Okay. So back to what I was saying. So here, notice that at time 1, you have A1, and then you keep increasing, adding G every single time period. Here, they say, in this special case, which is called a strict linear gradient, so keyword here is strict, the first payment at time 1 is actually going to be 0, okay? And then you just keep adding G. So it's the same thing, but except the first payment just like the series begins with a 0 at time 1, 0 payment at time 1. Now notice, of course, one thing here. G can be positive, which means that your payments are increasing. Oops, increasing. It can also be negative, and that's fine. And then your payments are decreasing. Okay? And of course, if it's 0, then that means your payments are just the same always. I mean, that's really not of interest. So either it's G is increasing, so here G is positive, or G can be decreasing, where you start with of course, in the strict, even in this strict case, you can have G being negative. So in that case, your payments are just going down, right? You're actually paying out of your pocket, for example. Okay. Oh. And of course, in most economic applications, this initial payment is not equal to 0, but we'll see why this sort of structure becomes very useful in the next few slides. In fact, in the next slide, I think we're going to see it directly, right? Usually in economic applications, the first payment is going to be equal to something, and then it's going to be increasing or decreasing. It may be equal to something, and then you start decreasing. But we'll see why this sort of strict linear gradient series is very useful. Okay. And so here's a linear gradient series, right? So this one here on the left. Now notice what happens. You can think of this as the composition or the sum of two different series. If you take this A1, so this initial payment, this is common to all of the payments that you're making across your time horizon. So you can just subtract or take out this A1 part out of all of these payments, and you get something that looks like this, right? So I'll draw a box around it. So this is one part of the payment. Okay, and so hopefully this is clear. But in addition, you have these extra increases. And so you can think of that as its own series. And after you subtract the A1, what's going to happen? The first payment at time 0 is just going to be 0. So that's the leftover part, right? The second payment at time 2 is just going to be capital G, and so on. You have 0G, 2G, 3G, 4G, 5G, and that's what you have here. And so this series that I started with, this linear gradient series, is actually the sum of two parts, right? So you have this part here, and you have the first part that we indicated. Now, what are each of these called? Hopefully you know by now. So can someone tell me what this series is called? Mazen?
The first one is equal payment series, and the second one is the strict linear gradient.
Yes, so this is equal payment series, and this is strict, I will just say LG, linear gradient, right? And so here's where that structure becomes useful, because our formulas work with this structure, with the strict linear gradient series. But even if I don't have the strict linear gradient series structure, what I can do is I can decompose it into an equal payment series, which I know how to handle based on what we covered in the last class, and this strict linear gradient series, which I'm going to show you formulae for. Okay. Now, what happens if it's decreasing? As I said, like the G can be positive, or G can be negative. In fact, here, like G is positive, but they're subtracting. But you can think about like this being a plus and G being negative. It's the same thing. So I'll just do that. So here they start with A1, but then the next payment is A1 plus G, where G is negative, okay? And it keeps decreasing until time period 6. So you can pretty much do the same thing, except now your equal payment series is going to be this initial A1. So it means you're actually like paying more in the equal payment series. And then you subtract, notice here what's happening. You have to subtract the gradients, the strict linear gradient series. And so the equal payment series looks different in the increasing and decreasing cases, but the strict linear gradient, like if G is the same, it's going to look exactly the same. Okay? The absolute value of G is the same, I should say, because I mean, I said G is negative here, but you know what I'm saying. Okay, so this is how we're going to deal with these types of series. If they're not in standard form, we're going to decompose them and then work with the parts and add or subtract as necessary. Right, so these are two strict gradient series, strict linear gradient series. Okay. Okay, so here's the part that's kind of important, the formula. So in the case of the strict linear gradient series, where my first payment at time 1 starts at 0, and then it keeps increasing with this value capital G, if I want to find the present worth, so again, we're working with factors, so present worth factor, right? So I want to find P at time 0, the present worth of this sequence of payments, I should use this formula, okay? And so this, of course, is a function of I and N, same as before. And you have to use G, right? So this is P, the present value given G. So notice here the change from what we had before, where we had either F or we had A, okay? And of course, from P, you can find F very easily if you want it. But I think the only formula that I'm going to show you is this formula for P, okay? So this, of course, gets a little bit more complicated. So that's why it's common to write this blue box as this part here. So I will say that this is G times, or yes, P given G, I capital N, where this part between brackets is exactly the blue box. And so instead of writing that formula every single time, I will just write it, which is exactly here. I will just write it like this. Okay? And so let's look at an example and see what's happening here. Suppose you're taking out a loan at time zero for $10,000, and the payments, for some reason, have to be made in a linear gradient series form, right? So the first payment is going to be for $1,500 at time one, but then you have to add some G, right, to each subsequent payment, and they keep on growing like you see here in the picture, okay? And so it's asking us, first of all, to find the remaining payments, right? And we're given I, which is not indicated on the graph, but we're given I, it says. We're also given N. So we're given the length of the payments, or the number of payments that you would have to make to repay the loan, and you're given the interest rate. And you're also given the initial payment. So this is A sub 1. So you see here, we're given A sub 1. So A sub 1 is going to be 1,500, right? And we're given P as well, because P is the amount that you're taking out in the form of a loan. And so what's missing is that we need to find G in order to find each of these subsequent payments, right? So because we know they're composed of 1,500 plus something, I need to find that something. So I need to find G, which is common to all of these blue arrows, okay? So that's what's missing. If I find G, then I find all the remaining payments that I need to make to repay the loan. And so based on what I said earlier, how do we go about this?
Decompose, doctor?
Yes, exactly. Because why do I need to decompose? Because my formula only works with strict linear gradient series, right? So I need to get a strict series somehow, which you can see here is this part, the blue part. And then the remainder is just an equal payment series, and I know how to work with that. And then I need to add the two together. And of course I add because the series is increasing, right? So my decomposition is gonna be these little black arrows. That's my first series. And the second one is gonna be these increasing blue arrows. Okay, so that's exactly what we should do, right? So this loan payment series consists of these two parts. We have a $1,500 equal payment series, and we have a strict linear gradient series, which of course, I mean, we don't know the G for, that's what we're supposed to find. And then if I compute the P for each of these two series separately, then I can add them together, again, because the series is increasing. If it were decreasing, remember in the decomposition, I would have to do some subtraction. Okay, and so here's exactly what's happening. So first of all, I know how to deal with my equal payment series, right? So to find the present worth of my equal payment series, which is this term here, remember from before, it's just A times P given A, that factor, for the given interest rate and the number of payments, of which we have 5. Okay, so this part should be clear. This is the equal payment series part. Equal payments, or equal series, I'll just call it equal series. Okay, so that's the first part. The second part is, of course, this strict linear gradient series. And for that part, the formula says I would need to do G times the factor, which is P given G. I would need to find the present worth. Okay, and so again, so this is, so there is a question. I'll just write strict LG. Mazen, yes.
Yes, doctor. And strict gradient. After finding solving for it, the arrow for it would be in period 5.
No, remember this is for finding the present worth, and so the arrow is going to be at time 0, one time period before the first payment.
Oh, okay.
And so that's a good point, because notice here that in both cases, in the equal series case, remember we said last class, the arrow for P is going to be one time period before the first payment. And also for the strict linear gradient series, the arrow is going to be one time period before the first payment. And so in both cases, the arrows are going to be here, which is good. That means I can add them without having to move anything afterwards. I can just add them directly. Okay. So let me remove the pen. Oh, and finally, of course, we need to set this equal to 10,000 because this is P. So I found the worth of my two series, and I know they're worth $10,000 today because that's the amount that I'm taking out in the form of a loan. And I would need to solve for G. Remember, we need to define G. Okay, and so now I just substitute. I plug in the formula that I have for this and the formula that I have for this, or you can use tables if you want. And after that, you notice everything is known except this G here. And so after that, it's just algebra, and I solve for G, and I find this value. So now, actually, if I were to complete the answer for the question, the answer like the question is asking me to find all of the other payments, I can actually write that A sub 1 is 1,500, A sub 2 is 1,500 plus G, right? Which I have the value for here, and then I continue. A sub 3 is 1,500 plus 2G. Okay, but if you find G, like you basically found all of them, but it's just making sure that you actually give the correct answer for the question. Okay, so hopefully this is clear. This illustrates how we can decompose a linear gradient series into an equal payment series and a strict linear gradient series, and then we can combine the two results together. Of course, you can also find these values in a table, the factors, right? And so if you look here, so we haven't gone over the table for a while now, but we've covered the single payment factors, the present worth, P given F and F given P. So we've seen those before. And then here, notice we have the equal payment series factors, which we did last class. I don't think I showed you a table last class, but they can also be found in the same table. So we had 5 factors, but remember the last one is for n going to infinity. That one really didn't need a multiplier. It's just, if you remember the formula for that case, it's just P is equal to A over I. So this is for the case that n goes to infinity. Okay, so we don't need, that's why we don't find that one in the table. However, for the other 4, you find them here with their names. Remember, sinking fund, present worth, capital recovery. And then finally, the gradient series that we covered. This one you can ignore, at least for now. I encourage you to think about what this is. However, I'm not going to go over this, but this is what we just did, right? This is P given G. So this is the gradient's present worth factor. And they only have these for linear gradient series. They don't have them for geometric gradient series. And maybe we'll see why if I remember to tell you why. But basically, the short answer is because there's another parameter there, which is little g, which complicates things because now you have an additional like parameter to look up. So they have n, they have I, they have little g, and they can't really present it nicely in the table. So that's why they don't have the geometric case. But this here is the linear case. So again, you can use that formula that I showed you. Or if you don't have it, you could look it up in a table. Okay. Here's another example, just to get you sort of more used to things and to see what's going on really in detail. So it's asking you how much you would have to deposit in your savings account right now, today, right? So it's asking you to find P at time 0 if the interest rate is 12% per year, and you want to withdraw these amounts from your account. You want exactly this pattern for whatever reason. Maybe it's to cover the cost of living, right? Because each year the cost of living increases. So you want to withdraw a little bit more the year after that. Okay, so first thing you notice is the difference between each 2 subsequent payments is $250. So what that means is I have G is equal to $250. And I have a gradient series, a linear gradient series. Okay, just make sure you verify that before you look at the first 2 and just jump ahead, right? Make sure it's always the same. It's always constant. And indeed, it turns out in this case it is. So in this case, all of these differences are $250. So I can safely assume that I have a linear gradient series. Okay? And I need to find P. So again, this is sort of P given G, right? Same thing we've been working with before. And so one way you can solve this problem is ignoring what I just told you today. So even if you don't quite get what's going on today, it's fine. And you can do the long approach, which is you take each of these payments and you move them back. You treat them as single payments, right? And we've seen how to do that. Hopefully you're all experts in that by now. You do that, and then you sum them all together, and then you find P, right? And so that's what this approach does. So this is the long approach. You take each individual payment, and then you find the present value given the F, right? So P given F, because you're moving right to left, okay? And then you move them. Of course, you have to be careful with the number of periods that you compute, and you find their values. And then, of course, what's left for you to do is to sum them at the end, and you find that the total is going to be this amount. Okay, so that's a correct solution to this problem, and that's fine. However, notice here that you had to do 5 sets of calculations, right? The other approach is to use shortcuts, which are always nice, and they get you the solution a little bit quicker. Okay. And so what's the other approach? Again, we decompose, right? This is a linear gradient series, but it's not quite strict. So what I need to do is I need to take out the equal payment series part, which is $1,000 paid every single time, right? And so that's what you see up here. And then what I'm left with is a strict linear gradient series, right? First payment is at 0, and it keeps increasing by $250, which is the value of capital G. And I need to find sort of a P1, which is the present value of this equal payment series, and I need to find a P2, which is the present value for this strict linear gradient series. And then I need to add them together. Okay, and we've seen how to do that before, right? So you take this equal payment series. I can use the formula for an equal payment series, and I find it's P1. If I do the same thing here, I use the different formula now for the strict linear gradient series that we saw in the blue box, right? And we find its value here. If I add them up, I get exactly the same answer. However, in this case, I only needed to do sort of big sets of calculations. If you like neglect or if you forget about just adding them as a third operation, which we had to do there, by the way. Even in here, like you still have to add. So you had to do like 6 calculations, whereas here you only had to do 3 if you want to think about it that way. But it gives you the same answer. So that's why like using these shortcuts, it's always nice. One more example for the fun of it. At least I think I only have one more. So here it's asking you which option is better. So remember, we're given 2 different alternatives. And so we're asked which one is better. And so in this case, the first one is to take a payment of $3.46 million today. The other case is to take an increasing, well, to take 175,000 right now. Notice here that this is a time 0. So it's not quite what we've been working with before, where the first payment always came at time 1. Okay, so just remember that. But after that, I'm going to give you $189,000, and I'm going to increase my payments to you every year by $7,000, right? G is equal to 7,000. Okay, so I'm going to give you this series after that. And of course, in order to compare these two and to find which one is better, I would need to compare them at the same time. And so because this one's already at 0, maybe that's more convenient for me to do. How do I do that? So of course, I only need to work with the second one. The first one's already at 0, so that's good. And the second one, notice here, I have my linear gradient series, right? But it's not quite strict. So I need to convert it into a strict linear gradient series, or decompose it into an equal payment series and a strict linear gradient series. And then, of course, I need to add the 175,000 because that's already at time 0, and that's kind of separate. Okay? And then if I do that, I get my 175,000 in the beginning, plus, and then, so this part comes from the equal payment series. As before, you see the A here. And then G times the strict linear gradient series present worth factor, right? So P given G. I compute that, I find it's this value here. And now what do I do? Because everything's at time 0, I can just compare the 2 options now. The option that I had from before, which as you see is 3.46 million, to the present value that I just found for the second option, which is 3.9 million, which is a lot better. And so I'm better off choosing this option here, option 2. Okay? Of course, this is just showing you that you can substitute in the formulas, which, I mean, so I think someone asked me either in this section or in the other section, if instead of writing the notation, you can substitute like in the formulas and show them on the slides. So this kind of does that here. It's the same thing that we saw in the previous slide. It's just showing you how to plug the numbers in. Okay, so that's all there is to know about linear gradient series. Now we're going to move to the second type of gradient series, and that's called the geometric gradient, as we saw before. Now notice here that, of course, well, first of all, let's remind ourselves what the difference is. So the difference is, in this case, is that after starting with the first payment at time 1 of a sub 1, your next payment is going to increase by multiplying it by percentage, right? So it's going to increase by a certain percentage, little g. Okay, and it's going to keep growing, and we said this is exponential growth. So it's not a linear, steady linear growth. Okay, and so this is showing you two cases. Little g is positive, again, as before, which means that this is an increasing geometric series. So this is growth, right? And in this case, g is negative, so this is decay. This is where you're losing money, I guess, fairly quickly. Okay. Notice here, because things are multiplied, it does not make sense to have a strict geometric series, because if you start the first payment from 0, the next payment is going to be 0 times some percentage. So that's also going to be 0. And so if you start with 0, you're going to have 0 all the way through. And so in this case, there's no decomposition. You always start with some payment in the first period A1. It doesn't make sense to have a 0 first payment in a geometric series or in a geometric gradient. And so what you'll care about maybe in this case is the formula. How do I compute the present worth or the present value for this geometric series or geometric gradient, sorry. And the answer is use this sort of complicated looking expression. And there are two cases here. One case is when the interest rate, is not equal to the increase rate or the decrease rate, little g. And the second one is when they are equal. And so just be careful about which one you use depending on the relationship between I and g. Okay. So here's an example, hopefully a very simple one. So you're given that little g is 5%, so that's your increased percentage. And then you're given that the first payment, A1, is $5,000. And the horizon is 10 years. Also that the interest rate is 7%. So see here, we have a little bit more to worry about. We have this little g, we have I, we have A1, we have N. And we're asked to find the present value. By the way, I should have mentioned this. Notice here in the factor, we have 4 things compared to the 3 that we had before. So we had I and N, these are always going to be there, right? We have A1, which is the first payment, and we need to find P given A1, right? And then we have this little g, oops. So this is also going to be in the factor. So the factor notation here changes a little bit. It doesn't have 3 things, it has 4 things because we have more inputs. So that's why there are more things to worry about in this problem compared to the linear gradient series. But the good news is that we don't need to decompose. We can just plug in the formula straight away. Okay, so in order to find P, we're just substituting the formula that I gave you before, given all of these inputs, and I find that P is equal to this amount. So this is just very straightforward plugging into the formula. Okay, so here's a more interesting example on this geometric series. Suppose you are retiring, right? And you get some retirement benefits. You get a pension each year. So that's the amount of money that the company will give you after you retire. And so in the first year, they tell you, I'm going to give you $50,000 over that whole year. And it turns out this amount is enough for the first year to cover your cost of living. You don't have to pay out of pocket or anything like that. Like it's enough for you to live. However, the cost of living increases each year by 5% because of inflation. So what that means is that in the second year, that 50,000 that they give me is not going to be enough to cover the cost of living because cost of living is going to increase by 5%. And unfortunately, the company will not adjust the benefits to accommodate or to cover the additional cost of living, right? So they're always just going to give you $50,000. It's up to you to sort of manage and budget and maybe pay out of your pocket in order to live comfortably. And so it says here, some of the cost of living, the additional cost of living has to come actually from savings that are different from what your company gives you after you retire, which is kind of unfortunate. Now, suppose the interest rate is 7%. How much would you need to set aside, right now, let's say, or how much would you need to have in order to meet this additional cost of living over the next 25 years? So at a first glance, like there's a lot of stuff written here, and it's always nice to translate this into a cash flow diagram. And so what we're going to do is we're going to plot sort of the inflow and the outflow. And so the inflow, the money that's coming to you, is going to be the retirement benefits. And so that's going to be $50,000 every single year for the next 25 years. And so that we can do, and I'll show you what it looks like on the next slide. Now, in addition, the outflow is expected to be your cost of living. It's how much you have to pay in order to live comfortably. And so that we can also kind of plot, right? However, that looks a little bit different because it's increasing from year to year. And so here's what both of them look like if I do them on the same graph, on the same cash flow diagram. So this part here is the pension, or the income that you get after retiring over the next 25 years. That's N in the problem. It's given us 25 years, right? So that's just a steady equal payment series of $50,000 every single year. However, the cost of living in the first year, the problem said that it's going to be enough. It's exactly enough to live comfortably, right? So I expect to pay $50,000 in the first year. Second year, however, it's going to be 50,000 times 1.05 because of that increase. And you see here, there's going to be an increase all the way to the very end, where notice here there's a big difference between the two after 25 years. And so if you look back at the question was asking me, how much should I have? How much extra do I need to meet this increase in the cost of living? So looking at this graph, how do you think I should go about finding that? Mazen knows. I want to give someone else maybe just a chance to see if. So a hint is to think in terms of inflow and outflow. So I have my inflow, which is the total pension over 25 years, and I have my outflow, which is this series, the series down here. And so what do I need to find the extra, or how do I find the extra that I need? I think Sultan had his hand up. Or was it Salman? Sultan, yes.
الدكتور نحسب المدفوع اللي بياخذه من الريتايرمنت والكوست اوف ليفنج نحسبهم بشكل متفرق، بعدين نطرح اللي ياخذه من اللي بيدفع حق الكوست ليفنج. اتوقع بيطلع كذا.
Exactly. However, next time please do try to say it in English, but you're absolutely right. I think everybody here is an Arabic speaker, so it works out just fine, but sometimes that's not always the case. But you're exactly right. So what Sultan was saying is that I can compute the worth of the income series on the one hand, and also I can compute the worth of the sort of outflow or payment series, the cost of living, on the other hand. And then I just subtract the two. Of course, I need to compare them at the same time period, so that's going to be 0. I think that's natural in this problem. And then I'm going to subtract them to find the extra that I have to pay out of my pockets, out of my savings, to cover the cost of living. Okay? And so that's exactly how you should approach it. And of course, we know how to deal with the income series. That's just an equal payment series of 50,000. So I just plug in the formula. I find this value. And the bottom one, of course, if you notice, it's just going to be a geometric series, a geometric gradient. I keep saying series because, I mean, geometric series is common in math, but this is a geometric gradient because this is not math, really. So this one, if you notice, is just a geometric gradient series with little g equal to 0.05, right? It's a positive 0.05 because this is increasing. It's not decreasing, okay? And so this I can treat using the formula that I just gave you, P given G, or P given A1 and little g, right? So P given A1, this is little g, this is I, and this is capital N. I plug in that formula, that expression, and here notice that I is not equal to G, so I use that part of the formula. I find this value here. So this is how much it costs me to live with inflation, with the increased cost of living. And of course, what's left is just I subtract. And that will give me the extra that I will need to set aside in order to cover this additional cost of living. Okay? Oh, so now, yeah, so that completes geometric series. So we've covered two types of series, and there are two, I think, additional practice problems also on geometric gradient series that I encourage you to look at. I think I just have the final answers for those in the slides. Like in the version that I uploaded, it has two additional slides with practice problems giving you the final answer. So make sure you go over those and you get the correct final answer. Now we're gonna just look at a bunch of problems. I have, 35 minutes, which is great. We're gonna look at a bunch of problems and we're gonna see how we can integrate sort of what we learned in this chapter together. So hopefully these few slides will make you more comfortable with the material and hopefully also with the homework. You should have everything you need to solve the homework completely at this point. The homework is likely going to be still due on at the end of day on Sunday, and we're going to have our quiz on Tuesday, next Tuesday. Yeah, a week from today. Okay. So, the title here is Unconventional Cash Flow Equivalence Calculations. So what unconventional means is that it's not really something that fits nicely into a pattern. It's kind of like that uneven thing that we saw before. In this case, it means it's not an equal series necessarily. It's like a mixture of different things. And we'll see how we can, even though it's a mixture, we can still do some smart things in order to avoid solving it the old-fashioned way by moving every single payment one by one. Okay, so I'm kind of jumping ahead already. So in this example here, I'm given this cash flow diagram, right? I'm given this series of payments or incomes. I know that the interest rate is 15%, and I need to find P. So at a first glance, you may think, oh, this is not an equal payment series. It's not a linear gradient series. It's not a geometric series either. I should resort to the old approach of moving everything one by one. And you can absolutely do that. That's completely fine, right? And so that's called like a brute force approach. You just take each payment individually and then you move it back, okay? And so looking at this again, is there a smarter way that maybe I can approach this problem? Yes, Khalid?
You can divide it into periods and take like from 5 to 8 as one equal payment and from 2 to 4 the same way.
Exactly. And so that's a nicer way of doing things, like using some shortcuts, and that means I have to do less calculations, so that's always good. And so notice, of course, that these two payments here are by themselves. Like these really don't fit into a nice pattern. So these I'm going to have to move individually in this case, right? But what Khalid was saying is that these here are equal payment series. They're like mini equal payment series that are hidden sort of in between the rest. I mean, they're not really hidden, but you get what I'm saying. And this one here is also another equal payment series. Now, before I actually show you what the solution is, just to make sure everybody's following and everybody understands what's happening, if I were to take this series here and apply the formula, what am I going to get? So remember, I'm going to apply the formula, let's say, for P given A. So I know my A, I know what the payments are, I know my I know N is 3 in this case. What am I going to get?
The worth at period 2.
So yeah, you're headed in the right direction, but not yeah. So I heard period 1. So period 1 is the correct answer here. So remember, the arrow for P in this case is always going to be one time period before the first payment. So it's going to be here. And so what do I need to do after that? Nazin?
Move it one period to the back.
Yes. Okay. So in order to deal with this block of equal payment series, I'm going to have to do it in 2 steps. it still saves me one calculation. Like instead of doing it in 3 steps, I do it in 2. You can imagine if the series was longer, it's going to save me even more. But I first compute P given A, but the P is going to be one time period before the first payment in the series. So it's going to be at time period 1. And then I'm going to have to move it back in order to compute the P that the problem is asking me to compute. So just be careful about that, okay? And now a similar thing happens here, of course. If I compute P given A for this series, one time period before the first payment, so it's going to be at time period 4. I don't know why I can't write today. And then I need to move it back. So how many calculations do I need to do? I need to move this payment here. I need to do 2 steps to deal with the equal payment series. So this is 1 and this is in 2 steps. And here I need to do 2 more steps to deal with this equal payment series. And then here I need to do 1 calculation. So total is 4, 6 instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if I counted correctly. Oh, or 9, I think. Mazen?
Yes, in the equal periods, in the second, in the $100 and the $150, I deal with them individually, like as if they're like, for example, in the $100, it says period 2, 3, and 4. I reset it to 0, 1, 2 in the formulas.
Oh no, so all the formula is going to ask you to do is plug in a value for I, which we know, a value for N. N is the number of payments, right? It's not necessarily the time period. Okay, I hope that answers your question. So instead of looking at this and saying N is equal to 4 and then thinking about resetting it, just count how many payments you have and then N would be equal to 3.
Oh, okay, now
does that answer your question? Okay, yeah. And so in this case, yes, go ahead.
When Ahmed.
Ahmed, go ahead. Sorry.
Doctor, when we calculate the present worth of the series of 150, we move it to the to the time period 4. Is that correct? We've moved it downward, so the net flow will be this value minus 100. Is that correct?
Okay. Not quite, because remember, we're not going to subtract, because everything here is basically going in the same direction. So even though I drew the arrow downward, you're actually computing the worth of these payments, right? And they're all income. And this is also income. This 100 is also income. So when you compute the worth of these 4 payments, it's going to be income. And this here is going to be income. So income plus income, like you don't subtract them from each other. The arrow I drew downward to keep with this convention here that you're actually depositing the money, but doesn't mean that you should subtract. So I do apologize if that created some confusion, but hopefully what I just said clears it up. Because everything is just income, we're just going to add everything. There's no subtraction here. We're going to see actually an example later where we might need to subtract, where something really is in a different direction. But in this case, we don't. So does that clear things up?
Yeah, Doctor, thank you.
Okay, you're welcome. All right, so I'll show you really quickly what the slide is showing, which is exactly what I told you. We just group them into these groups, and we move the first and last payment separately, and then we treat these ones in between like equal payment series. However, it's kind of small. I can't even see it on my screen. I don't know if you can, but notice here that we have 2 factors, because we said we're going to do it in like 2 steps. I mean, here they do it in 1 step. You can just multiply everything, which is fine. But really the nice way to think about it is in 2 steps, right? You compute the present worth given A, and then you move it back to time period 0. And here you do the same thing. And then of course we add everything together at the end. Again, like I said, because this is all income, it doesn't really matter where the arrows are. And we find the value. Question, Khalid?
Yes, Doctor, isn't it better instead of moving group 1 first, do group 2, then sum the amount at period 1, then move it at once?
Oh, yes, absolutely. That's a good point. So Khalid is saying, so I'll switch to this picture just because it's clear. You do this first. right? And then you get the present value. So I'm going to draw it down, but I mean, you really should add them. Okay, I'll draw it up so that it doesn't cause confusion, right? And you compute, let's say P1 or whatever for these payments, and then you add these two up and then move them back together. So that's even better than what the slides have, right? And you should get the same answer. Okay. Of course, you don't want to do the same thing here, maybe, because if you compute the P here, it's going to destroy, and you add it to the 100, it's going to destroy your equal payment series here. So you don't want to do it here, but here it's absolutely fine. So hopefully everybody sees what I mean by this. But what you said, Khalid, is absolutely correct, and should give you the same answer, and it should maybe even save you a little bit of work. Okay, just to move on. So I have roughly 10 slides left. Should be good with time. So here's another example. Suppose a person makes 4 annual deposits of $100 in their savings account. Okay, and I know that the annual interest rate is 10%, but the question is asking me, if I want to withdraw this money after it grows over 4 years in equal amounts and equal withdrawals, how much would those withdrawals be? And so here's basically what the problem is saying. I mean, sometimes the pictures is a lot easier to digest, but you should be comfortable, hopefully, with reading this, understanding this, and then translating it into a picture, into a cash flow diagram. Okay, so in this case, I is 10%. So let's see what's happening. First year, you're depositing money, right? So I'm making 4 annual deposits of $100 in my account. I want to withdraw that money over the next 4 years, 4 subsequent years, right? But I want to withdraw it in equal amounts. So I want to withdraw it in equal amounts A, where A is unknown at this point in time. And so notice here that this cash flow diagram, and this kind of hints at the question about the arrows, right? So this cash flow diagram is from the perspective of me, or of that person who's making the deposits and withdrawing the money. I can think about this same problem, and the calculations will be the same, but from a slightly different perspective, which is sometimes called the economic equivalence perspective or point of view. And so here, notice that the question is phrased a little bit differently, but really the core of the problem is exactly the same. It's asking me, suppose I have 2 options, let's say, right? So I'll call this option 1. Oh my God, I don't know what's going on. Option 1, and then option 2 down here. Option 1 is receiving equal payments of $100 in the same time periods as my deposits, right? So this is sort of this part here. We're kind of splitting these into 2. Okay? What about option 2? Option 2 is receiving these equal payments in the same periods as my withdrawals, which are 5 through 8. Again, you see here, 5 through 8. Okay? Now, because here in this diagram, these are sort of, hold that thought, never mind. Okay, let's go back here. So notice what the question is saying here. So it's saying, what is the value of A that will make these 2 things equivalent if the interest rate is 10%, which is exactly what we had in the previous problem. So if you think about it, this is the same problem phrased in a different way, in a different perspective, and that's why all of the arrows here point up. But notice here, of course, that we're kind of splitting them, we're separating them. And so we're given one cash flow, which is up here, and we're given a second cash flow, which is down here, and we're sort of asking an economic equivalence question. When are the 2 equivalent? Because it's an equivalence question, I mean, it's the same thing happening here. When are my deposits equivalent to this withdrawal series? Okay, so hopefully you see the point that I'm making. The question is the same, it's a question of equivalence, but here I kind of split it into 2 cash flows, as if someone was offering me 2 different options, 2 different cash flows, and I need to pick. Okay, and that's why the arrows here are pointing up, because I mean, someone's offering me this money. And by the way, we already saw something like this with the loan example, with the college loan example. I think a student, I think it was in this section, asked me like, why are the arrows pointing upward even though it's a payment that's supposed to go out of your pocket? And the answer is it's a matter of how you frame the problem and how you what point of view do you want to take. But they should give you the same answer as long as you're careful and you understand what you're doing. So this is the solution to that problem if you use the first cash flow diagram, right? And so what we need to do is, as before, this is an equal payment series. I need to compute its present worth. This here is like this income series is also an equal payment series, but with A, so I don't know A. I need to compute its worth. And then because I'm asking for the economic equivalence between the deposits on the one hand, which are here, so deposits, and the withdrawals, I should set them to be equal, right? So this amount of deposits will give me exactly this amount to withdraw. And so because I need to find A, I will move these guys, these four, at time period 0, and I will get a downward arrow. So that's the worth of these payments. I will move this up here at time period 0, sorry, by doing it in 2 steps as before. Remember, the P is going to be here. It's going to be at time period 4. This is getting a little bit messy. And then I move it back 2 steps, right? 2 factors. You see here, this is the first factor, and this is the second factor, right? And then I need to compare them to find the equivalence. What value of A would make my deposits equivalent to my withdrawals? And if you solve for A, you find that A, I think it's in the next slide, or maybe not. Yeah, I don't think they have the final solution, but you can just divide. A is just 316.99 divided by 21651, right? After you set them equal, you can just solve for A very easily. Okay, so here we did the economic equivalence at time 0. We moved everything back to 0. Of course, you can also do it a different way by moving everything to time period 4. So what changes then? So what changes is, first of all, for this series here, you don't need to move it back anymore, right? Because when you compute its present value, it's going to be here. It's going to be here. So you just apply the formula, which is right here. Sorry, this is not for this one. Erase pen, right? You apply the formula here, right? So you take the individual A's, you don't know what they are, and you apply the present value given A formula with the interest rate and with the number of payments equal to 4. And you find this expression containing A. Now, what about these guys? These guys are a little bit different, because if I want to compute it at 4, that's not P anymore, that's kind of F. That's the future value of these payments at time period 4. Now remember, with F, we said the F that you compute using the formula is going to be exactly at the payments, at the last payment. So F is going to be here. So remember, P comes one time period before the first payment, F comes exactly at the last payment. So in that case, you just plug in the formula for F given A using 10% and 4 payments, which we have, and you will get exactly F at time period 4. And so that's in a way, this approach is easier because you don't have to move everything. You don't have to move anything after you do the first computation. Everything just falls into place, right? Your P is exactly where you want it to be at 4, and your F turns out to be exactly where you want it to be, which is also at 4. And then you compare the two, you set them equal, and you should get the same answer. Okay. Here's another example. So this is a retirement example or an investment example. So it's saying, suppose you have 15 years left until you retire. And in each of those 15 years, you're going to deposit an equal amount to contribute toward your retirement fund. Okay, so an IRA is I think it's an individual retirement account. It's a type of account that they have in the US. So if you don't have to worry about what it is exactly, just know that it's like a retirement fund. Okay. And so the first deposit is going to be made at the end of year 1. And so that's what you see here in the graph, right? 15 years, you're making equal payments. Now, you need to save enough to make a series of withdrawals. And unfortunately, the withdrawals are increasing because of the cost of living, let's say, right? So G is 4%, so that means each withdrawal that you make afterwards, after the 15 years, is going to increase by 4%, right? In line with the increase expected in the cost of living. And your last withdrawal is going to be at the end of year 25. And so it's asking for the following. It's asking you to find C that sort of covers or makes this withdrawal series possible, assuming that the interest rate is 8%. Okay? So this is kind of similar to what we've seen just now. So there's an inflow series and there's an outflow series. And I just need to be careful here because I can't just add like things together without being sure of what I'm doing. And in fact, what I need to do is I need to find a point, for example, 0, and find the present worth of this series, this inflow series, right? And I find the present worth of this outflow series. And I need somehow the inflow and the outflow to be equal. So I need to solve for C that makes these two equal. Okay? So that's one way to do it. In fact, that's the approach they take here. In the first part, they do the economic equivalence at time period 0. But you can also pick a different time period, and I think we'll see that in the next slide. So how do they do it at 0? First of all, they find the worth of the equal payment series, right? So it's C, which is the unknown payment, and then I find P given A with the interest rate that was given in the problem, and I have 15 payments. If you remember, this equal payment series has 15 payments. I plug in, I find an expression with C in it. What about the withdrawals, right? So this is the other side. So this is for the errors that are going up. Well, there I need to do it in like 2 steps. So let me erase this. So first of all, when I compute P for this series using the formula for, remember this is geometric, so the formula is going to look like this. It's going to be P given A1, and then little g, which I know, which is 4%, I, and N. Okay, so if I plug that in, I find P is going to be here, right? And I can draw it up maybe just to emphasize that this is different from these guys, right? I don't want to confuse anybody. So I'll draw it up. So this is going to be P prime, let's say. But then what I need to do, of course, is I need to move this back all the way to 0 because I'm making my comparison at 0, right? And so that's what's happening here. They first compute the geometric part, find what that is worth, and then they move it back 15 years, right? So this here is 15 years back. And that gives me the equivalence, or the equivalent for that series, for the geometric series, or for the series of withdrawals. Now, what I need to do, because of course they're at the same time period, I can compare them. And what I need to do specifically, because one is income and one is outcome, or payments, I need to set them equal to each other and then solve for C. And if I do that, I find that this is the value of C. Okay? So you can go over these details later. Hopefully at least the concepts and how you should approach the problem is clear. Of course, you could have done the equivalence at a different point in time, right? And so in this solution, they say that you could have done it at time period n equals 15. And so let's see what 15 looks like, first of all, before we... So 15 is here, right? And so in order to do the equivalence here, for this part, for this series, you just have to plug in the formula and that's it. It's going to give you the correct P, right? So P is going to be here. What about for this series? Well, now instead of P, I need to compute F. And F turns out to be at time 15 because that's when I make my last payments. That's when F is, right? So my F is going to be here. So in this case, I didn't have to move anything, right? I just compute one time for this series, and I compute another time for this series, and I find two values. I set them to be equal, and then I solve for the unknown value of C. And you see here, we got 2894. If you take this other approach at time 15, you get exactly the same answer, which is 2894. Right? So you can be smart about like which period you want to pick, and sometimes that will save you a lot of time in calculations. And maybe it helps you also make less mistakes if you do that. I have a few more examples. I have like 3 more. So here's an example where the interest rate changes from time period to time period. Now, if you remember, in general, if you have a single payment series, in order to find F, you will apply this formula, right? Which you've hopefully memorized by now. But this kind of assumes, and I think someone raised this point either in this section or the other section, that I is always the same from one year to the next. What about if I is different? Right, so here notice that the interest rate changes from year to year. From year 0 to year 1, the interest rate is 5%. And then it grows to 6%, and then it goes back to 4% for the last 2 years. So how do you think I should go about solving this if I wanted to find F for these payments? Yes, Ibrahim?
The average of interest rate.
Actually, that wouldn't be, that may give you like an approximation, maybe, but that's not an accurate solution. And And you'll see why maybe. Like when someone suggests the correct answer maybe, or I go through it, hopefully it makes sense. So Mazen, and there was someone else. Give me a second, Mazen. Oh, Khalid. Okay, Khalid, go ahead.
You can do the same thing, divide them as periods, take the 6 alone and 4 alone, and also move the 5th, the one with the 5%.
So you're saying do them one by one?
Take the ones with the same percentage, with the same interest rate, the 6% and the 4% and the 5% each alone.
So keep in mind that this payment, for example, it has 6% for 1 year, and then it has 4% for 2 years. So like it doesn't have an interest percent of its own, right? It's not. I'm not sure if I maybe understand what you're saying, but hopefully you see my point. If what you're saying is what I think you're saying. So let's see. So Mazen, let's see what Mazen has to say first, and then.
I think if, like, for example, if we take the $300, we multiply by 1 plus 5% to the number of periods it has. Multiply also by 1 plus 6% to the number of periods in this example 2, and also for the 4% interest.
That's the correct way to do this. And what Mazen was saying is, well, that's one way actually. I mean, I'll show you a slide that's a slightly different way from what you were saying, Mazen, but the outcome should be the same. So what Mazen was saying is that you take your $300. I know it grows at a rate of 5% for the first year. So what I can do is I can find 300. How much it's going to grow by 5% in 1 year, right? And so that's going to give me something here at time 1. But then it grows at 6%. So what do? I just multiply this, right? This amount that I got at time 1 with this for 2 years, because it grows at 6% for 2 years. And I keep going like this. And then I do the 500 in the same way. So it's going to grow at 6% for 1 year. And then it's going to grow at 4% for 2 years. So I'm going to multiply that, whatever value I have at the beginning, with 1 plus 0.04 to the power 2. And then finally, I do the 400 by itself, which is just what we've been used to. So that's one way to do it. So you kind of do it by hand, right? You have to do it one by one, step by step, because the interest rate changes. Okay? And so here's what I have in the slide. So it's kind of similar to what Mazen was saying, except I do it really from one time period to the next. So basically what I do is I move this 300 one time period, so it accumulates interest at 5%, and then I grow it by 6%, and then I add it to the 500 that's here, and then I take them together. So that just saves you a little bit of work. So if I go back to the slide, so I take my 300, I move it one time period at 5%, and I get this amount. If you guys remember the table that we saw in the beginning of this chapter, this is kind of the same thing. And then I take my 315, I move it forward by one time period at 6%. So if you see here, one time period, 6%. And then I add the 500 to it, because now I found this other payment at time 2, and I can like take it with me. I can carry it along. And then I do the same thing. I move the combined total one time period at 6%. There's nothing to add there. And then I continue in the same way, and then I find my final answer. Okay, so because the interest rate is different, we can't use that formula. We can't use like the shortcuts that we have in the formulas. We have to be careful and do it like almost by hand, step by step. Okay, so here's an interesting example that I want to make sure I go through before I run out of time. And that is, what about here in this case where you have what looks like an equal payment series, but we're actually missing a payment. Okay, and you want to find P, and we know what the interest rate is. So everything is given, and you can of course do this by hand, one by one, but you have 15 or 14 payments, sorry, and so that's a lot. And so ideally I want to have an equal payment series, and then I could do it in one go, but I don't have an equal payment series. So one approach to do this is what we've seen before, and I'll just go over it quickly, is just to break this down into 2 parts. Is to do this part here, right? Find its P, and its P is going to be here at time 0, which is good. And then work with this part here, find its P, right? And so its P is going to be here. And then I need to move it back to time 0. Same thing we've been doing before, and then I add them up, and that's my P. So that's one approach. Is there another approach that you guys can think of, just real quick, Mohammed?
Can we assume that this payment is available, then we do the calculation the regular way, then subtract this this payment and its contribution?
It's good to hear from someone other than Mazen and Khalid. Not that I don't like hearing from them. So thank you, Mohammed. So that's exactly right. So what we can do is we can assume that this payment exists. So I add an arrow here. But I also need to subtract it. So you can do it like you said, Mohammed, maybe like think about the subtraction at the very end, or just to make sure you don't miss it. When you add this payment, you subtract it as well, right? So it's balanced. It's almost like 0 payments, right? And then I have my equal payment series. I just have to worry about this extra thing that I have, and then I'm gonna subtract it, of course. So make sure you add it to the cash flow diagram so you don't forget. So you don't forget about it, okay? And so if you see what this looks like, just real quick. So again, yeah, we pretend that we have the 10th payment, and we have to subtract it or like put it on the other side. I mean, it depends on like which perspective you're taking, right? And so that means I haven't changed anything, just like in math, where you add and subtract a value to make something work, right? And then I manipulate, I work with the equal payment series, and I can find its P, but then I need to be careful, like Mohammed said, I need to subtract the worth of this $100. So I need to also move this $100 here, and then I do the subtraction, right? And so that's exactly what's happening here. I mean, the way they write it is a little bit different, so I encourage you to see what's happening here. But it's basically P is equal to the equal payment series, whatever that's worth, which is this value here, minus the worth of the 100, which is this value here, right? So minus the 100. I'm kind of sketching things here for you so you can see what's going on, right? And hopefully that makes sense. So after you move them, you subtract them because they're in different directions, and then you find your correct P with less calculations and hopefully less steps than you would have done otherwise. Okay, final example. I think we're doing great on time, so that's good. So this is, again, an unconventional or irregular cash flow pattern. Suppose I have an equal payment series, but it's not every year. It's every 2 years, right? So each time I'm paying C, but instead of paying it every year, I'm paying it C every 2 years. So it kind of looks like an equal payment series, but not quite. And I'm given an interest rate, and I'm given, let's say P, in this example, and I need to find what C is. So how do I deal with situations like this? Any ideas maybe about what to do so I can make life easy for me? Of course, as always, you can just move individually. You should always be able to do that, even if you're stuck. As long as you don't have a lot of payments, you should be fine. But is there maybe a smarter way that you can think about, at least an idea, even if it's not like concrete, and we can refine the idea? Any suggestions? Yes, Mazen?
Yes, we can do it. We can assume that equal payment in every period. And then we add the period 1 and period 2, move period 1 to period 2 and find the sum. And we can, because it's equal, we put the same amount in every 2 periods.
Are you saying like we should follow the approach that we did in the previous problem? Like assume we have it equal and subtract it? Or
subtract? I mean, if we do assume it's equal, and we find the amount in each period, and then each 2 consecutive periods, let's say for assume period 1 and period 2, we move period 1 to period 2, and the summation is in the second period, and we do the same, yani, for each 2 period, I think.
Then you're adding arrows here, but like that's not like you're adding stuff that you shouldn't be adding.
No, I mean just period 1 and 2. If we add them, and the amount would be equal in period 4 and period 6 without doing other calculation, I think.
1, right? So I think what you're saying is you add here you add, so I have a minute left, so I have to be quick. So you add something here, and then you move this here, right?
Yes.
And I think you're kind of getting at what I had in mind. It's just like the way you're saying it maybe is a little bit different from what I would have expected. So let me just hear from Abdullah real quick, and then I have to tell you the answer, and then I'll let you go. Abdullah?
Is it correct if I just add the interest for 2 years instead of 1 year, and then I do the whole calculation?
No. So you have the right sort of idea, but you can't add them. Okay, so here's what the solution actually looks like. Or here's one way you could do this. And hopefully this is what Nazim was saying as well. So what if I modify the interest rate? Instead of this I, what if I find some I prime that applies every 2 years instead of this I being for every 1 year? So this is kind of what you were saying, I think, Abdullah, but you don't add them. So let's see if we can find that. And if you think about it, it's going to be this. You're going to take the multiplier for the first year, 10%, and then multiply by the multiplier for the second year, 10%. So if you think about it, this is how much your balance would grow over 2 years if your interest rate is I equal 10%. Think about it just with $100, right? After the first year, it's just going to be 110, 10%. After the second year, it's not going to be 120. You can't just do 20%, right, of the 100. It's going to be 10% of this, which is going to give you 121. So really, in effect, your money has grown by 21%. Okay, over 2 time periods. And then I just sort of rename my periods so that I have an equal payment series, but now I use this I prime, which is for every 2 years. Okay, and I can solve for C. All right, and so that's the last thing I have to say about this chapter. It was a long chapter. All the other chapters should be shorter. If you have access to the textbook and you want a little bit more, you want to solve problems or whatever, so this was chapter 2, and you can read it from the textbook. Otherwise, I will see you guys next week. Remember the homework, and be ready for the quiz on Tuesday. Have a good weekend. If you don't have the book, that's fine. Muhammad's saying we don't have the book, that's fine. If you do, it's great. If you don't, everything that's important from the book should be in the slides, so don't worry about it.
دكتور الهوم ورك عن chapter 2 كله ولا إلى مكان معين؟
And the quiz is going to be all of chapter 2 as well.
لا الهوم ورك.
Both of them.
معلش دكتور متى راح يكون الكويز؟